So these voltages
Sir,
would
me
be
what?
phase to neutral AC voltages only if the AC neutral is physically connected to the midpoint of the DC voltage. Okay. So this is, it should be actually in the previous figure I shown you like these waveforms. So DC current from phase A, DC current from phase B, DC current from phase C, and total DC bus current. And next last one is DC current with unity power factor inverter operation. Okay, and now so based on those, so at any time three valves. So actually we are taking the valves. So here we have three valves. So one valve containing one thyristor and one diode connection in parallel. So here I am taking the three valves. So at any time three valves are conducting in a three-phase converter system. Okay, so in fact only the active power part of the AC current and part of the harmonics flows into the DC side. Okay, that is already shown in the figure. So actually in this one it should be noted that the square wave waveforms of VA, VB, VC are the phase terminal voltages with respect to the hypothetical midpoint N of the DC voltage and not the neutral point of the AC side. Okay, so here so these voltages would be phase to neutral AC voltages only if the AC neutral is physically connected to the midpoint of the DC voltage. So in the previous class I show in one circuit diagram for the three-phase full bridge converter. So in that one we have the phase to neutral AC voltages connection. So these voltages would be phase to neutral AC voltages only if the AC neutral is physically connected to the midpoint of the DC voltage. So in the diagram, the AC voltage, the AC point, the AC side point A or B is connected to the physically connected to the midpoint of the DC voltage. So whenever the phase to neutral AC voltage, whenever the neutral is physically connected to the midpoint of the DC voltage, these voltages would be phase to neutral AC voltages. Okay, so in which case the converter would in effect become a series connection of two three-phase half-wave converters. Actually, in this case, I am dealing with the three-phase full-wave bridge converter, but so in which case the converter would in effect become a series connection of two three-phase half-wave converters and not a six-pulse three-phase full-wave bridge converter. Okay, so here in this case I am taking that for a square wave with amplitude of Vd by 2. Okay, for a square wave with amplitude of Vd by 2, the instantaneous values of VA, VB, VC based on Fourier analysis. So here we are using the Fourier analysis concept for the square wave with amplitude Vd by 2. Here I am taking that the instantaneous values of VA, VB and VC based on Fourier analysis are given by. So here I am taking the one equation. So that is the Fourier transform, that is VA is equal to for one phase. So VA is equal to 4 by pi into Vd by 2 cos omega t minus 1 by 3 cos 3 omega t plus 1 by 5 cos 5 omega t minus 1 by 7 cos omega t. So this is the instantaneous value of VA by using the Fourier transform method. Okay, this is for phase A, voltage at phase A. So VA is equal to 4 by pi Vd by 2 cos omega t minus 1 by 3 cos 3 omega t plus 1 by 5 cos 5 omega t minus 1 by 7 cos omega t plus and so on. So here VA is obtained by replacing. So this is the basic equation, fundamental equation. So by using that equation, we have to obtain VA. So VA is obtained by replacing omega t by omega t minus 2 pi by 3. Okay, and VC is obtained by replacing omega t by omega t plus 2 pi by 3. So based on these two, we will replace the equations like this. So here for all triplet harmonics, that is third, ninth, that means multiple of 3. So 3 into 3 like this. We will take the triplet for all triplet harmonics, that is third and ninth, the multipliers 3 comma 9 and so on in the terms like this: cos 3 of omega t plus or minus 2 by 3, cos 9 of omega t plus or minus 2 pi by 3. So that is the triplet harmonics. Okay, plus or minus means if we take the VA, that is the voltage at phase A. So at the time I will take omega t minus 2 pi by 3. So if we take VC, so that means omega t plus 2 pi by 3, like that we will take, and so on. Okay. So if we want to reduce these terms to cos 3 omega t, so actually in the previous case I am taking these three, cos 3 of omega t plus or minus 2 pi by 3 and cos 9 of omega t plus or minus 2 pi by 3. But here to reduce these terms to cos 3 omega t, so which means that all the triplet harmonics of all three phases are in phase. So if you want to reduce these terms to cos 3 omega t, so which means that all the triplet harmonics of all three phases are in phase. Since the AC neutral in a bridge converter is floating, actually the AC neutral in a bridge converter is floating, so it is necessary to work out phase to neutral voltages. So those are which appears across the transformer secondaries, that is in the AC side. So we are taking the transformer at the AC side only. That's why since the AC neutral, okay, since the AC neutral in a bridge converter is floating, so it is necessary to work out phase to neutral voltages which appear across the transformer secondaries. Okay, next, if it is assumed that the three phases are connected to a Y transformer secondary, that is a Y connection is star connection. Okay, so if it is assumed that three phases are connected to a Y transformer secondary with floating neutral, so floating neutral is common, that is the neutral is common, so then the floating neutral will acquire a potential with respect to the DC midpoint, which is 1/3 of the sum of all the three voltages of phase terminals A, B and C. So these A, B and C are all connections of the AC side. Okay, so if it is assumed that the three phases are connected to a transformer secondary, that is a star connection with floating neutral, then the floating neutral will acquire a potential with respect to the DC midpoint, which is 1/3 of the sum of all the three voltages of phase terminals A, B and C. Next, so if you see this diagram, so this one, so here so it shows a Vn, that is the neutral point. Okay, the figure shows that Vn is a square wave of magnitude Vd by 6 with 3 times the frequency, that is it has all the 3n harmonics of the terminal voltages. Okay, 3n harmonics of the terminal voltages that will show in the that shows on the Vn waveform, square wave with magnitude of Vd by 6. Next, subtracting Vn from the phase terminal voltages with respect to the neutral give the phase voltages across the star connected transformer secondaries as shown only for the VAN phase A to transformer neutral voltage in the figure. So actually in the previous class I showed that one waveform, operational waveforms of three phase full wave bridge converter. So in the diagram in the last we have three waveforms. So in those waveforms we have Vn voltage waveform, that is the neutral voltage, neutral voltage wave, neutral point voltage waveform, and next phase to neutral voltage waveform. So based on those two waveforms, here I am subtracting the neutral point voltage, that is the Vn, from the phase terminal voltages, subtracting the Vn from the phase terminal voltages with respect to the neutral, give the phase voltage across the star connected transformer secondaries as shown only for VAN. So in that waveform we are taking that VAN waveform, so that gives the VAN waveform, that is phase A to transformer neutral. phase A to transformer neutral, that is combined, that is VAN. So it consists of steps of VD by 3. So actually that contains of stepwise manner. It contains a square wave, but it is in the stepwise manner. So it consists of steps of VD by 3, a 6 pulse waveform free from 3 n harmonics. So actually the 6 pulse waveform free from 3 n harmonics. So already I said that from the figure, Vn is a square wave of magnitude Vd by 6 with 3 times the frequency. So it consists of steps of Vd by 3. Okay. So a 6 pulse waveform free from 3 n harmonics. So it now has harmonics of only the order of 6n plus or minus 1. 6n plus or minus 1, that is 6n plus or minus 1 means that is 5th, 7th, 11th, 13th, etc. Okay. So if the order of harmonics is 1, that is 6 into 1 plus or minus 1, that is 6 minus 1, that is 5, and 6 plus 1, that is 7, and 11, 13, etc. 6 into 2 plus or minus. If the order of harmonics is 2, that is 6 into 2 plus or minus 1, that is 12 plus 1, that means 13. 12 minus 1, that means 11. So like that we have the order of harmonics, that is 6n plus or minus 1. If it consists of steps of Vd by 3. Okay, and the 6 pulse waveform free from 3 n harmonics. Next, we will take the waveforms Vbn and Vcn would be the same. Like VAN, we have the VBN and VCN also, but here these are all same, but except phase shifted by 120 degrees and 240 degrees. 120 and 240 degrees, here the phase shifting by the, but from VAN. From VAN, it will phase shifted by 120 and 360 degrees respectively. Okay. And next, so note that AC phase to neutral voltages. Note that the AC phase to neutral voltages are still in phase with the AC phase to DC neutral voltages, that is VA capital N and VAN. So VA capital N means the AC voltage with neutral point. Okay. Note that the AC phase to neutral voltages, that is VA capital N, are still in phase with AC phase to DC neutral, that is VAN, are in phase. The only difference between VAN and VAN, that is VA capital N and VA small n, is that VAN is with the triplet harmonics of VAN. So VAN contains the triplet harmonics, but VA capital N does not contain the triplet harmonics. So it is shown like that. So that is VAN is equal to 4 by pi into Vd by 2. So this Vd by 2 is the voltage. Okay, magnitude of voltage, that is Vd by 2 into cos omega t plus 1 by 5 cos 5 omega t minus 1 by 7 cos omega t minus 1 by 11 cos 11 omega t plus 1 by 13 cos omega t cos 13 omega t, like this and so on. So these are the triplet harmonics. So I already said that the VAN is with the triplet harmonics. That means we contain this waveform, that is omega t 1 by 5, 1 by 7, 1 by 11, 1 by 13. Already I said that in the previous case. So if you see this one, so it contains 5th, 5th, 7th, 11th and 13th harmonics, okay, etc. Here I am adding this one in this one, that is 4 by pi into Vd by 2 into cos omega t plus 1 by 5 cos 5 omega t minus 1 by 7 cos omega t minus 1 by 11 cos 11 omega t plus 1 by 13 cos 13 omega t plus and so on. Like this we have the VAN. Next, the phase to phase voltage waveform VAB shown in figure 3.4b, that is in the previous class I shown the operational waveforms of 3-phase kilobit converter. So here I am taking that the phase to phase voltage waveforms like VAB, VBC and VCA. You know that. Okay, the phase to phase voltage waveform VAB shown in the figure is also a 6 pulse waveform, but of different wave shape than VAN. Okay, so depending upon this, apart from the observation that VAB is a 2-level voltage, actually it contains 2-level voltage with 0 or VD. Okay, 0 or VD. This is the 2-level voltage. And VAN is a 3-level voltage, that is 0, 1 by 3 VD and 2 by 3 VD, 3 level voltage. Okay, comparison of waveforms VAB and VAN shows that the two are phase shifted and VAB is larger than VAN. Okay, so we are taking the taking that the apart from the observation that VAB contains two level voltage. It contains the values of voltage that is 0 or VD, and VAN contains three level voltage levels that is 0, 1 by 3 VD and 2 by 3 VD, and compare these two VAB and VAN shows that two are phase shifted and VAB is larger than VAN. Okay, being face to face voltage that is VAB or VBC or VCA, being face to face voltage, fundamental component of VAB is phase shifted by 30 degrees. So the fundamental component of VAB is phase shifted by 30 degrees and its amplitude is V3 times the VAN. V3 times the VAN. Then the RMS value of the face to face voltage that is 120 degrees. It gives V is equal to root of 1 by pi integral minus pi by 3 to plus pi by 3 VD squared d omega t, that is equal to root 2 into VD by root 3, that is equal to 0.816 VD. So this is the RMS value of face to face voltage. VAB or VBC or VCA. This is the RMS value. Okay, V is equal to 0.816 VD. 0.816 VD. And next, so the value of the fundamental and harmonic components of the face to face voltage is given by, so here we have the fundamental and harmonic component of face to face voltage, that is VAB. In this case I am taking the VAB. We know we have VBC and VCA, but here I am taking that VAB, so that is equal to 2 root 3 by pi into VD into cos omega t minus 1 by 5 cos 5 omega t plus 1 by 7 cos 7 omega t minus 1 by 11 cos 11 omega t plus 1 by 13 cos 13 omega t minus and so on. So here the RMS value of fundamental is given by V1 is equal to root 6 by pi VD, that is equal to 0.78 VD. So V1 is equal to root 6 by pi VD, that is equal to 0.78 VD. This is the RMS value of the fundamental. Okay. Next. So compare it to the total RMS value including harmonics. Okay, compare it to the total RMS value of the 0.86 VD. Individual harmonic voltage is given by Vn is equal to V1 by N. So this is the individual harmonic voltage formula. Vn is equal to V1 by N. Okay, compared to the total RMS value of 0.816 VD. So the value of fundamental and harmonic component of the phase to neutral voltage. So in the previous slide I am discussed about VAB, that is the phase to phase voltage. Here in this case the value of fundamental and harmonic component of the phase to neutral voltage is given by VAN is equal to 2 by pi VD. VD is the magnitude of voltage, that is the voltage value on the DC side. 2 by pi VD into cos omega t plus 1 by 5 cos 5 omega t minus 1 by 7 cos 7 omega t minus 1 by 11 cos 11 omega t plus 1 by 13 cos 13 omega t plus and so on. So here note that the VAB and VAN. So VAB means phase to phase voltage and VAN means phase to neutral voltage. So are defined above with their own zero reference. Are defined above with their own zero reference, and in fact the two are 30 degrees out of phase. These two are 30 degrees out of phase. Okay. Next, so the figures, that is the, in the first slide I have shown the waveform. So based on that, the DC side current waveform, those are all DC side current waveforms. Okay, so consider the first, the waveform IA for current in phase A. I already said that. So the entire figure shows the DC side current waveforms. Okay, consider the first waveform, it is IA, that is DC current from phase A. Okay, for current in phase A shown in figure, that phase B. So this current flows through the phase leg with valves 1 to 1 dash and 4 to 4 dash. So I already said that on the diagram. It contains 1 to 1 of valves 1 to 1 dash and 4 to 4 dash. And next, reversing the waveform sections of 4 to 4 dash gives the DC current contribution of the phase leg A. So reversing the waveform sections of the valve 4 to 4 dash gives the DC current contribution of phase leg A to the total current in the DC bus on converter side of the DC capacitors are as shown by the top waveform in figure 3.4c. The top waveform, that is the phase A to DC current from phase A. So in that one I am reversing the waveform sections of valve 4 to 4 dash only. It gives the DC current contribution of phase leg A. Okay. Next, contribution of current from other two phase legs is shown by the next two waveforms. That is DC current from phase B, DC current from phase C, those two waveforms. So contribution of current from the other two phase legs is shown by the next two waveforms. Okay. That is DC current from phase B and DC current from phase C. So adding up the three currents gives the total DC current. Okay. Adding up the three currents gives the total DC current ID. That is the fourth waveform. So adding those three, that is a DC current from phase A, DC current from phase B and DC current from phase C. Add these three waveforms, we will have the total DC current. So adding up the three currents gives the total DC current ID in the DC bus. That is the fourth waveform. And next, it consists of direct current component. So you already know it consists of direct, that is the DC component, and harmonics of the order of n is equal to 6k. N is equal to 6k. That is 6th, 12th and 13th. That is 6 into 1, 6 into 2, 6 into 3, 6 into 4, 6 into 5, 6 into 6 and so on. Like this we have, it contains the harmonics order. N is equal to 6k. Okay, next the direct current component of this current is given by ID is equal to 3 root 2 by pi into I cos theta, that is equal to 3 root 2 by pi means 1.35. So if you solve 3 root 2 by pi, it will give 1.35 value. So ID is equal to 1.35 into I cos theta. 1.35 into I cos theta. Next, so here I is the RMS AC phase current and theta is the power factor angle. So from this equation, I is the RMS AC phase current, I is the RMS phase current and theta is the power factor angle. So here the current is maximum at 1.35 I. So the current is maximum at 1.35 I when the power factor is unity. Okay, when the power factor is unity and changes from plus 1.35 I2 minus 3.5 and vice versa as the angle changes from full rectification to inverse of power. Okay, actually the current is maximum at the value is 1.35 into I, that is when the power factor is unity and changes from plus 1.35 to minus 1.35 and vice versa. Okay, as the angle changes from full rectification to the inversion of power. Next, nth harmonic current is at its minimum when power factor is unity. Okay, now nth harmonic current is at its minimum when the power factor is unity and corresponds to IN by IDM, that is equal to root 2 by n square minus 1. This is the formula. So in this one, IDM is the peak value of the DC bus current. IDM is the peak value of the DC bus current. That is the peak value means we have 1.35. That is the peak value of the current, DC current. And increases to maximum when the power factor is 0. And increases, that value is increases to maximum when the power factor is 0 and corresponds to this one. That is IN by IDM, that is equal to root 2 n by n square minus 1. In the previous we have root 2 by n square minus 1. So in this case we have root 2 n by n square minus 1. That means the higher the value of n, the lower is the harmonic amplitude. Okay, the higher the n value, the lower is the harmonic amplitude, and clearly the three-phase full wave converter has much lower harmonics than the single phase full wave converter. Okay, because of the elimination of low order and other harmonics, particularly the second harmonic. So we don't have the second harmonic. Okay, that's why the three-phase full wave bridge converter has much lower harmonics than the single phase full wave bridge converter because of the elimination of low order and other harmonics, particularly the second harmonic. And next, however, even in a 6 pulse operation, the second harmonic will reappear. The sixth harmonic will reappear. So the second harmonic will reappear during AC voltage unbalances, and the system needs to be designed to suppress or ride through low frequency harmonics during AC system faults and other reasons for system unbalance. Okay, next. Thank you. So that's all today.